And welcome back. And in this video we're gonna take a look at what I will call, or what not I only, but other people also call Softmax Regression. And this is the extension from the logistic regression model if we have more than two categories. So we are in a situation where our target variable is of categorical nature, but has more than two categories. I don't know. You can encode them depending on if you want to, but I think initially or per intuition we typically, if we encode variables with multiple categories, like in 1, 2, 3, for instance. I don't know, and this doesn't mean that there's some ordering here, right? So it doesn't necessarily mean that this is an ordinal, the variables of ordinal nature. So we can have red, blue, and green, and we may encode it in red is 1, blue is 2, and green is 3, okay? And we can, for instance, considering stocks, we can either buy a stock, we can hold a stock, or we can sell a stock. Okay, so we can have more than two categories, and our target variable is encoded in some form into a number, where each number represents a specific category. And now the question is how to best predict which category we will observe for a corresponding observation. So again, we have feature variables as always. They provide the information and bring the conditional perspective. So conditional on specific realizations of the information, which is presented by the feature variables. We try to make a prediction which tells us what category is the most probable, okay? Which has the greatest likelihood. And this already indicates how we're going to model it. So as before, we were questions only how can we make such predictions? So how do we need to define our model in order to generate such predictions? And how can we train such a model, which again will be, of course, be calibrated by parameters. So which is the appropriate loss function to calibrate such a model? Okay, so yeah, very similar to the situation before. Before we had two categories, now we have big K categories if we have this in general, and we will have a vector for each observation with probability predictions, and we have a probability prediction for each category. So given like some information, for instance for a stock, we will have the probability for what's best. So the probability for buying the stock, the probability for holding the stock, and the probability for selling the stock. Okay. And this is our probability vector. And again, the categories, they are disjoint, which means that summing over all these individual categories needs to sum up to 1. And as we have probabilities, each individual probability needs to be greater or equal to 0. And okay, so how will we define this model? First of all, let's go directly to an example. Let's assume we have simply two feature variables for a specific observation. So the realization of the first feature variable is 1, and the realization of the second feature variable is 2. Now what we're going to do is, in the first step, use the linear prediction function of the linear regression model, but we will use it for each category. So for each category, in the first step, we will generate a real valued number, and those numbers only differ because we will use different parameter estimates for each category. So that is why in this matrix here, we have in each column the parameters that correspond to the specific category. So if we have 3 categories, then in order to generate the real valued number out of which we will make the probability prediction for the first category, we will use these 2 parameter values. Okay, so multiplying 1 with -1 and adding 2 multiplied with -2 ends up in the real valued number -5. And here the parameters that correspond to for making probability predictions later for the second category are given in this column here. So here it is only 0 and 1, so only 2 remains, which is why we have the value of 2 here. And here are the parameter estimates not the estimates, here are the parameter values for the third category. So we have 1 times 1 plus 2 times 2, so we have a value of 5. Okay, so the idea here is for each category we have a specific parameter vector, and subsuming the 3 vectors for the 3 categories, we have a matrix for a single observation in order to generate 3 real valued numbers. And now the only thing that we need to do in order to make probability predictions out of these 3 real valued numbers, we need to transform them again. Not in the same way as for the logistic regression model, but the basic or like the general idea behind it stays the same. So we need to find a function in which we can plug in these values and which outputs values that match our needs. And our needs are that each of these values will be greater or equal to 0 and below 1, because it's a probability, and the sum over all these probabilities will sum up to 1. And the function that we are going to use will be the Softmax function. So what it first does, it use the real valued numbers here in the exponent, and as here typically the Euler number for the base here. So this makes a positive value out of set, no matter if it has been negative or positive before. And we do this with each real valued number that corresponds to each category. So first of all, this makes sure that we have only positive numbers, so that they are above 0. And now that in the end they sum up to 1, we use the sum over all these real valued numbers, positive real numbers, in order to normalize it. Okay, I think it will definitely get clear if we directly jump to the example here. So what we do here, for instance, we have these 3 real valued numbers, which we have seen before, how they are generated and how they're calculated. So this is the normalization here, and now for the category of 2, which was the second category, we had a real value of 2 here. So we have it up here. Okay, so this makes sure that it's positive, and this makes sure that it in the end normalizes to 1 if we sum up over the probabilities. And this is how we generate our probability prediction. Now, for instance, for the first one, we would have E and then in the exponent -5, but the normalization here stays the same. And here for the third category, we have E and then 5 in the exponent, okay? And this results in the probability prediction. And this is how our model works. So this is how we would start from the feature variables using parameters to make a prediction vector, where at each position we have a probability prediction that corresponds to the probability of this observation belonging to category 1, 2, and 3. Okay, and this is basically how we will generate our predictions and how the model works, and what we refer to as Softmax regression. And we refer to it because the function that we use to transform the real valued numbers to the probability is called the Softmax function. So now we can take a look at the general setting here again. So we'll discuss this in a second, but we will have for k categories a probability vector given in feature information and some parameters that gives us a probability prediction for each category. And in order to generate these probability predictions, we will need a matrix for each observation, or not for each observation. The matrix will be used for each observation, and each column here matches the parameters for a specific category. So if we calculate this here, then it generates a real valued numbers, and then we use the Softmax function as we've seen in the example and generate the probability predictions. Okay. Now the next question is, and how are we going to calibrate these parameter values? This question is basically the same as questioning which loss function should we use, should we minimize in order to calibrate the parameters. And this is now the same as for the logistic regression model. So what we will use is minus log of the probability prediction of the category that we're actually observing. Okay, and in order to calculate this more easy, we will use a one-hot encoded vector of the target variable. So what is this? We already introduced it in the last video, I think. But if we have, for instance, like 4 categories, which is as corresponds to the example here below, then we would have a vector for each observation with zeros everywhere except for the place where the actual category matches to. Okay, so if we have 4 categories, then we need for each observation a one-hot encoded 4-dimensional vector, and at the position which matches the category that we observe in reality for this target variable, it has a 1 here. So if we have like 1, 2, 3, 4 categories, and this observation in reality would belong to the second category, then we would have here the 1. If it would, for instance, belong to the 4th category, then this would be a 0 and this would be 1. Why do we do this? In order to easily calculate or easy to get the probability prediction for the category that we're actually observing, because assume now if we have here our probability vector, and if we calculate the dot product of the one-hot encoded target vector and the probability vector, so if we do this here, then we have 0 times the first probability prediction plus 1 times the second probability prediction times 0 plus 0 times the third, and so on and so on. So what only remains if we calculate the dot product of this one-hot encoded vector and the probability prediction vector is the probability prediction for the category that we actually observe with respect to the training data that we use. And now, so this is what we can see here. Yeah, this is how we calculate the dot product. And what you have here are always zeros except for the category that we're observing, which then leads to the fact that only the corresponding probability prediction remains. So if we would do this here in another example, we have again a 3-dimensional one-hot encoded vector, and the category for the target observation or for the target variable that we have for this observation is the 3rd category. So, and we have these 3 probability predictions that we derived before. Now calculating the dot product, then we have only the 3rd probability prediction. Sorry for that. Here we need a 3, of course, not a 2. And this value is entering now the loss function for the specific observation, but not directly with the probability, but with minus log of the probability. And that is, let's take a quick look here, because we're using this function here because it makes sure that if we have a high probability prediction for the category that we're actually observing, then it is good because we have a low value for the loss function, and a low value always is a feedback that this is a good prediction, and obviously it is a good prediction if we have a high probability value for the actual category. But if we have a very low probability value for the actual category, that means we would predict that this is the category with a low probability. This is something that we do not want for a model. We want the opposite. So then the feedback would be a higher number here, which enters the loss function, which again then will tell our optimization, hey, please change this to a higher probability prediction in order to minimize the loss function to have a better model, which actually outputs high probability predictions for the categories that we're actually observing. Okay, so this is the idea here. And as always, we're not only doing this for single observations, we will calculate these for all observations and average this. So on average, we want to succeed in having high probability predictions for the categories that we're actually observing. And this is, I think, quite intuitive, even though it may, here written down in this way, may seem to make it more complex. But what we really ask for a model is, please, if it is category 2, then make a prediction which is high, indicating us that it is really category 2. And if it's category 1, then please generate a probability prediction for category 1 which is high. Okay, so sounds intuitive to me. Good. Okay, so now we have seen how we can handle typical regression tasks. So basically what we need to do if we have a target variable which is a real valued number. We have seen what we need to do when we have a binary target variable, and we have what we need to do when we have a target variable with more than 2 categories, but which is of categorical nature. But the latter was, there will be only one category that is realized. In reality, even though this does not happen that much, to be honest, it may also be possible that we are interested in having a target variable which can be multiple categories at the same time. Okay, so assume we have, we are observing 3 different stocks, and we encode it in this way that we say, okay, either we sell the stock, which is a 0, or we buy the stock, which is a 1. So it may be a situation where we want to have, 1 0 and 2 1s, indicating that we will sell one of the 3 stocks and buy 2 of the other stocks. And with all you heard so far, you can do this simply by combining the idea of the logistic regression model and the softmax regression model. So let's just only quickly take a look, because as I said before, we will, not, to be honest, in my experience, this is what we will not see many times, or we will not face this kind of task too much. But I think from a didactic perspective, it kind of is good, because it makes sure that you really understand the basic principles that we learned so far. Okay. So, for instance, we would be interested in vectors like this, as I already talked before here. So, first position here is either 0 or 1, 0 indicating we should have sold the stock. Then 1 here tells us that we should have bought the second and the third stock. And in this way, we can observe, like we would take historical data and get target vectors for each observation. And for instance, the feature vectors could be, the closing prices of these stocks from the day before, or other variables which may provide more information regarding future developments of these stocks. So as for the softmax regression, we would also need a target, or we need predictions that correspond to probabilities for each category here. But now we will do, we mix the things that we've seen before. So what we will do is, in the first step, we will do basically the same thing as for the softmax regression. So we will generate for each observation 3 real valued numbers. And then we will use the function that we used for the logistic regression model in order to generate a specific probability prediction for each of the 3 values here. But each probability prediction just tells us do or do not something. And this is the situation from the logistic regression model. So we will use the logistic or the sigmoid function in order to transform the real valued numbers. So as from the example from the softmax regression, starting from some feature variables and a parameter matrix, we will end up with 3 real valued numbers. And now if we insert each of these real valued numbers into the sigmoid function, then we will have 3 probability predictions. Now the summing over these will not lead to a value of 1, which is okay, because that's exactly not what we're looking here for, because at each position, for instance, we could make a decision rule, like if this prediction is higher than, 0.5, then we will do as told. So if it's higher than 0.5, we will buy the stock, and if it's below, then we will sell the stock, okay? And in order to train such a model, we can do the same thing as before. So here we have a different encoded vector, and we will multiply each of these positions with the probability prediction. So we have the dot product here, and we will use, again, as for the cross entropy, minus log of these probability predictions. So, and again, for the corresponding 0 or 1 categories, you can take a look at this example on your own, and you will see it basically is again like the combination from what we've seen before. And yeah, do not I don't know, get scared by this stuff. It is just an extension of the idea of the logistic and the softmax regression, and if you do not understand it for the moment, it's not a big deal, because as I said before, typically we will deal either with binary or category or multi-class classification. But this is how we could further extend the idea of the binary and the multi-class classification models if you would have situations where we have so-called multi-labeled data or multi-label regression, how I would call it then. So this is just an extension of the idea from the models that we've seen before. Okay, so this is how the models work, and now you have the possibility to gather a basic understanding what needs to be done for each of the three tasks that we maybe face. And now this is already quite a lot, because always the important part, at least when it comes to modeling, and modeling is only how can we generate the predictions and how should we calibrate the model. The things that you've seen here can be done in different ways, but the principles stay the same. So if we have a regression type problem, no matter how we construct the prediction function, the output should be a real valued number. If we have a binary classification problem, no matter how you define the model, it should typically generate probability predictions, but typically in binary classification models, you have a single probability prediction corresponding to the probability for the target variable being the category of interest, and the remaining part, so 1 minus this probability, is then the probability for the other category. And if we have more than two categories, usually we will have for each category a probability prediction, and this has the demand for that probabilities have, so being greater or equal to 0, being below or equal to 1, and if we have disjoint categories or possibilities, then summing up over all individual probabilities will need to be equal to 1, okay? And the loss function that we've seen here can always be used to also calibrate models that are, have a different architectures than the models that we've seen. But the idea is to use loss function which are suited to provide a good feedback if this is a good prediction or if it is not. Okay, and when it comes to feature importance, we have different possibilities, and the possibility that we've seen here so far is to, in your head, you should assume that there is already an estimated model. So the parameters value are now given, and then we are wondering the prediction function, how sensitive is it with respect to changes in the feature variables, and we assume that if it's very sensitive, then we assume that also the feature variable is quite important for the model, and if the model works good, important for the model also means it is important in reality. Okay, now as we have the base classes of typical tasks that we are going to be confronted with, in the next video or videos we will take a look at some things that need to be considered typically even before estimating the models, and some pragmatic things which can help you also to improve the modeling side. So be excited about it, as I am always, and see you in the next video. Bye bye.